This video is going to cover the next section of Chapter 5, Indefinite Integrals, but we're going to start off with a little warm-up. So what I want you to do is go ahead and pause the video and do this linear approximation video, and when you get done, you only need about half a sheet of paper. When you get done, hand it into the box. We are not going to go over the answers. This is going to be kind of like a target check, so hand it in on a half sheet of paper. So you can get your notebooks out, and this is the beginning of section 5.3, Indefinite Integrals. And the first thing we're going to do is a little recap on antiderivatives, because we did a little bit of this in chapter 3. And just kind of want to recall, if f prime of x equals ax to the nth power, what does f of x equal? And so if you think back to when you find derivatives and you're using power rule, you bring the power down and multiply it by whatever constant's out front, and then you reduce the power by 1. And so if you're going in the opposite direction, instead of bringing the number down and multiplying, we're going to take the previous number and divide it, and then we're going to add 1 to the power. And so this is the antiderivative that we've been using the most with practicing antiderivatives. We've just been using the power rule. Remember, when you're doing antiderivatives, to make sure you have that plus c at the end. And so what this video is going to incorporate is antiderivatives of functions that aren't in the form that we can use the power rule. So just for a little practice, you can go ahead and pause this video. I want you to determine the antiderivatives of each of the following functions. So you guys are given f prime. I want you to find f of x. And in the fourth one, you're given a point on f of x, and you need to figure out what that is used to solve for, and then come back to the video to get the answers. So for number 1, f of x equals 2x cubed plus 4x squared minus 3x. Don't forget your plus c. Number 2, you can bring your derivative, or the x to the third, up to the top and use x to the negative third, and then use the power rule that way. And then I just simplified my antiderivative so that it didn't have any negative exponents. Number 3, this one you had to be careful because this one also incorporated a chain rule. The derivative of the inside was 3, so not only do you have to divide the number out in front by the previous power, you also have to divide the number in front by what the derivative of the inside is. And so 18 divided by 3 is 6, but then 6 divided by the previous power, 6 is 1. So my constant out in front is 1, and then add 1 to the power, and then your plus c. And then just remember, you could always check your work by finding the derivatives of these. So then if I did chain rule, I'd bring the 3 out, bring the 6 down, that would make 18, 3x plus 7 to the 5th, and then my derivative of my constant would be 0. And then in number 4, you were given a point on the graph, and that was used to help you solve for c. So then you probably changed your square root to the 1/2 power, did the antiderivative rules. Your simplified answer, this could have also been x minus 5 to the 3/2 power. Your c value should have been 50, and that's what it looks like in simplified terms. So section 5.3 is indefinite integrals, and there's going to be a little bit of new notation, but essentially you're just going to be finding antiderivatives of different functions. And so now we're going to get into functions other than just those where we're using the power rule. So for instance, what's the antiderivative of cosine of x? And other trig functions, other exponential functions, logarithmics. So first, just with a little bit of new notation, the way that we write what we call an integral is g of x equals, then there's this skinny little s. It actually kind of looks like an f, a cursive f, but without the line through it. That's called an integrand, and that's a symbol, but the whole thing reads g of x equals the integral of f of x dx. And so if you remember from earlier days, we've been finding the differential dy, and we've been multiplying both sides by dx. This is the reason you need to have dx on the right-hand side now, because all integrals will be sandwiched with an integrand followed by a dx. And so this is the integral of f of x dx if and only if g prime, so if you were to take the derivative of the left side, you also have to take the derivative of the right side. Well, an integral and a derivative cancel one another out, and so you'd just be left with f of x. And so remember, that little symbol is called an integrand. It is an operator, so it's telling you what to do. So it's kind of like a plus sign, a minus sign, division symbol, and it's pretty much just telling you to find the antiderivative of f of x. And then dx is the differential. And that just tells you with what variable to work with. So there might be a time where it might be a dy here, a dt, a dv, and a du. So that tells you just with what variable are you doing the antiderivative of. So we're going to go through a couple of different properties. Some of them are pretty self-explanatory. They're similar to other properties that we've used before. So the first one is the integral of a constant times a function. So we are going to say that k is a constant, and we're taking the integral of k f of x dx. Well, that k can just come out in front, and then I just need to find the antiderivative of f of x, and then multiply it by k. So for example, I have the integral of 5 cosine of x dx. Since 5 is just a constant, it's not part of the derivative because there's not a 5x here. I can move that 5 out in front, find the antiderivative of cosine of x, and then multiply that antiderivative with 5, and then just don't forget to put plus c at the end. So we get 5 sine of x plus c. The integral of a sum, this could also be, or a difference of two or more functions. So when you have the integral of f of x plus g of x or f of x minus g of x, you can split that up into two different integrals, and then just find the antiderivative of each one independently, and then add them together or subtract them. For example, if we have x to the fifth plus secant squared of x minus x, I can split this up into three different integrals and find the antiderivative of each of them. This is one property where you don't have to do this. You can just find the antiderivative of each part. But it's a property that we will be using a little bit later on more and more. So the antiderivative of x to the fifth, just knowing your power rule, the previous power was to the sixth, so multiply by 1/6. Secant squared is the derivative of what? Trig function. I should have said tangent, and then minus the antiderivative of x, that would just be 1/2 x squared. And then don't forget your plus c. So if you did each of these individually, you would have a plus c at the end of all of them, but when you're adding three constants together, it just creates one new constant. So I want to go back to the integral of secant squared of x. So how did I know the antiderivative of it was tangent and not I didn't have to use the power rule here? So why isn't the integral of secant squared x dx, why doesn't it equal 1/3 secant cubed of x plus c? Why doesn't that power rule apply here? Well, one thing you want to start recognizing derivatives, and I recognize secant squared as the derivative of tangent. But let me show you, if you were to do the derivative of 1/3 secant cubed, okay, you've got a chain rule involved. So 3 times 1/3, that would cancel out to 1. Then you'd have secant squared, but then don't forget the derivative of the inside would be secant times tangent. And so the derivative, secant tangent times secant squared, is not what I had after my integrand signed. Had I had the secant tangent in front, then we could have used the power rule for our secant squared. But we'll get into more complex integrals a little bit later on. The integral of the power, this is the one we've already talked about. Even if there's a constant out front, that number would be here instead of the 1. So just the x to the 9th, the antiderivative would just be 1/10 x to the 10th plus c. And then the other one that you want to be careful about with the power function is when there's a chain rule. And so you'll want to remember to divide by not only the previous power, but divide by the derivative of the inside. So the derivative of the inside would be 7, so 1 divided by 7, but then also 1 divided by the previous power was 6. That would leave me with 1/42, 7x plus 4 to the 6th power, and then your plus c. The integral of the natural exponential function, so just e to the x. So just remember, this one was nice and simple. The derivative of e to the x was just e to the x. But then make sure that you are also paying attention to if there had been a chain rule. So in this instance, we have 2e to the 2x. And so there's another function inside the exponent. Its derivative is 2. So I would have to divide by whatever that derivative is. So 2 divided by 2 would just be 1. That leaves me with e to the 2x plus c. Had this been a 10 out front, I would still do 10 divided by that derivative up front or up top, so that would be 10 divided by 2, and so I'd have a 5 e to the 2x. And then just remember, a way to check your work would be find the derivative of that function, and it should be whatever follows that integrand symbol. The integrals of other exponential functions that don't have a base e. So remember, the derivative of b to the x is b to the x times natural log of b. And so because there isn't that natural log of b here, I need to divide by that. And so if you were to do the derivative of this, the bottom is just a constant, so it would just be b to the x, because the natural log of b's would cancel one another out. So the example I have here is 5 to the x. So just following this, since I don't have the natural log of 5 with it in my answer, it would be 5 to the x over natural log of 5 plus c. So the integral of 1 over x. So does anybody recognize this as a derivative of a function? This is one where you can't bring the x to the top and use the power rule, because this would be x to the negative 1. And if you think about what the previous power would be, if I were to add 1 to that exponent, I would get x to the 0, which would just be 1. And this is not the derivative of 1. So 1 over x, if you recall, is the derivative of the natural log of x. But you have to be careful here, because think about the domain of 1 over x. 1 over x is a hyperbola. It has vertical asymptote at 0, and it has a horizontal asymptote at 0 as well. But you can plug in every single x number except 0. So you have a domain of negatives and positives. So its derivative also has to have that domain. And so when you write the antiderivative of 1 over x, you have to include the absolute value bars. If you didn't, you would just get the natural log of x, and that limits your domain to only positive values. And so taking a look at the graph, on the left side here we have natural log of x. It's just going to be positive values, because you can't take the natural log of a negative number. But when you include the absolute value bars around x, so when you do have a negative x and it makes it positive, this is what the graph looks like. And so the derivative would incorporate all x values just not equal to 0. And so make sure when you guys are doing antiderivatives of 1 over x, you are including those absolute value bars. You will lose points if you don't include those absolute value bars. And then the last one I have is when you do have an integral of 1 over x to the n, where n doesn't equal 1. So if this had been 1 over x squared, 1 over x cubed, with that one, you can bring the bottom up to the top with negative exponents and then just use the power rule backwards. It just doesn't work with 1 because you make it x to the negative 1 and its previous power would be 0. So that's the only one it doesn't work for. But all the other ones, you can just bring them to the top and use power rule. So here I have 1 over x squared. I can rewrite that as x to the negative second power, and then just using power rule, divide by, my previous power was negative 1, so divide by negative 1. Add 1 to the exponent, you get negative 1, and that leaves me with an antiderivative of negative 1 over x. And I made the cardinal rule of forgetting my plus c, but make sure you have a plus c at the end of your answers. Okay, so you're going to go ahead and pause the video for these 8 practice problems. I want you to work solo on them for a little bit, and then you can pick a partner and work for a few more minutes, and then Mr. Harsty has the answers and he can go over them with you. And then before you pause the video, here is your assignment. It's page 196, 27 to 39, multiples of 3, so starting at 27, so 27, 30, 33, etc. And same thing on page 202, 3 to 33, multiples of 3, and yes, I will be collecting this assignment. So go back to this slide, pause it, and do these practice problems of finding indefinite integrals. Have a good day.